Welcome to numerical ship and offshore hydrodynamics. Today is the lecture 45. Today we are going to continue discussion on the previous talk. So, previous class we have discussed that some basic mathematical formulation. Now, today again we are going to discuss only the numerical part of it, like it's big and it requires some time to do, but today also in surface level we are going to discuss that what is the approach to solve this time domain panel method. Okay. Now, and also these are the keywords that we are going to use to get this lecture. Now, let us try to uh, figure out how we can solve the time domain panel method numerically. Okay. Now, remembering that we are not going to discuss the theory is already discussed many times, and in last class also some of the theory we have covered, uh, but today uh, we try to address numerically, or we try to attack this problem numerically and trying to find out the solution. I mean, not trying to find out, but the surface level discussion, as I said, like what would be the approach to get to the solution. Okay. Now, you can see that first you started with the hydrostatic calculation. Now, these hydrostatic calculations are very important because it is in time domain why these hydrostatic calculations and correctness of the hydrostatic calculations are very important. Let us briefly discuss first. Now, suppose this is your some mean line, let at z equal to 0, there is no waves, and then you have a ship the top of it. So, this is the pure hydrostatic condition, like at z equal to 0 with the mean sea level, and at t equal to 0 we assume that there is no waves, and then it is in static position. Now, this is the physical phenomena, and that you need to confirm through your numerical coding. That means, in numerical coding under these circumstances, that your weight mg should be okay, let me write it bigger way, that weight mg, right, should be and then this is the upwards force, which is rho g z, and if you integrate this over the surface dz, which is the buoyancy force. So, you can call the F b, both should be the same, or we can say F static. So, static force and the weight should be balanced each other. Now, this is very important. Suppose if it is not, then what is going to happen? Let us say in some way your code is not performing fine, like you are taking that m as the input, you can take this mass as the input, right, and you calculated somewhere that input, right. And then when you do the hydrostatic calculation like this thing, then you get some the buoyancy force F static, and both are not equal, F static is not equal to mg. So, if it is not equal to mg, then what happened at t equal to 0, either your ship as a initial some downward force because of the weight, or it could be some upward force. So, what is happening if you try to plot the graph at t equal to 0? So, at initially it has an impulse, a static impulse, either this side or that side, which is not desired, right. So, that is how actually one should be very careful when even they started coding, he has to confirm that at static position everything is fine, right. So, this is actually I just explained why it is so important to get your basic hydrostatic calculations done. Now, there are many ways you can do this hydrostatic calculation, like you can take our so called what I say, like in hydrostatic, that so called conventional method, for example, you can have, let us say, this top at z equal to 0, you get this water plane, right, you can find out, and then actually you can integrate this, so you can get that water plane area, right, and then then again you can try to figure out that what is the value for Ixx, area moment of inertia, and Iyy, and then actually through this actually you can find out what is the coefficient, then C35 or C55 etc., or C44, this coefficient. So there is a way to do this, right. However, when you using this panel method code, from the beginning what you have is the panels, right. So beginning what you have, if you use this panel method code, okay, let me draw a very simplistic 3-dimensional geometry. You can basically, this is called the wiggly hull. Okay. So from the wiggly hull or so whatever the thing, anything that if you started with a panel. Now see, it is a very it is not very smart way to figure out that what is the value of water plane area, what is the value for C35 or C55 etc., using this the panels, right, or the weighted area, right. How we calculate the weighted area normally? Now when you calculate the weighted area, what actually the normally we are going to do from the hydrostatic table or the offset table, suppose is given to you. So then normally what you people do as follows. So they are having as I said, offset table. So they are having with respect to, here you can call x1, x2 and xn, and then you have here z1, z2, and then different draft level. So in different draft level, what we are having is the y. So if you fix your some station x1 and if you vary your depth level, so this may be the corresponding to x1, and this y1, y1, let us say y11, y12 etc., is basically nothing but this distance along the z. So this is the distance, this is your y point, and this is the graphical representation of this rho, right. Now what is happening normally, how to find out that weighted surface is nothing but you find out the length of this. Okay. Now if you find out the length of this, so then what is happening from along the length, so along the length, and if you find out the length of this, so if you this L, that the length in the sectional length, you can call this sectional length, then again you might have some kind of a graph like this, right. Now if you have this graph with you, and you can simply do the trapezoidal or Simpson, whatever, you can get the surface, I mean the area, right, the length. Now if you do this continuously along this the line, then definitely you will get the surface area. So what is happening in this particular x, you have this length, this particular length you have this length, that particular length you have then this length, and then you are integrating along this x. But this is all, it is fine when you do not have the panels. Now fortunately we are having panel, so therefore the whole exercise become very easy. How? Let us see. Now again I am drawing the same simple shape. for clarity. I could use this, some graphs also, but I thought this is fine. So, suppose this is you have the panel, right. Now, if you remember, we have already discussed how to get the area of a 3-dimensional surface, planar surface. So, now if you have this x1, y1, or let us say, let us give it a point p1, p2, p3 and p4, and all these points are, let us say, a 3-dimensional surface p x y z, then we have already discussed from this 3-dimensional thing how to transfer back to the some 2-dimensional arbitrary plane. So, it is, you can call this small p 1, small p 2, small p 3 and small p 4, right. And then this all this small p is only the function of x y, right. So, then and also remember that what we have done is, now we have very simply we know the how to find out the area of a quadrilateral. So, if you do this area of a quadrilateral, so we know the area of each panel. So, now if you sum of this area of the panel, if then actually you can get the weighted surface area. So, you see, I really do not need to do all this exercise. I am just calculating this from this offset table, what is the length of each section, I mean the sectional length. In fact, just again this is the sectional length, if just L1. So, I just calculate L1, L2, L3, L4 and so on, and then I just integrating it, it is really time consuming. However, once you have the panel, it is simple, just I try to find out the panel area. So, then I do this integration or the summation, I will get the surface panel, I mean the weighted surface. Now, this is one how I get the panel area. Now, second is that how I get the water plane area. So, what is the water plane area? Now, if this is my ship, again I am doing the paneling. Okay, I can have one more here, this is better. Just trying to keep the aspect ratio is good. Yeah. Now, since this is again a this thing. So, what I try to figure out that what is the water plane area. So, this how to get this water plane area, right. Now, it is also very simple, frankly speaking. Now, you try to find out that panel area, it is I can call this area panel area multiple by n z, and this will get some number and can call this is your, let us say, B. So, it is B I equal to A I into n I z. So, what I am getting, that I am getting that area of the ith panel and I multiply with the n z, that vertical component of that area. Now, if you, that means the vertical projection of the area. Now, if we add this B I, then this gives me the value for the water plane area, right. You check that it is very easy to see as in case of a 2-dimensional body. Now, suppose this is your line and then this is the shape of the curve, and then you are distributing it number of panel in 2-dimensional case. Now, what you are doing is you take this and then you take the vertical projection of this length. Now, if you take this vertical projection of the length, then it gives you this much of length. Then again you take this and again you take the vertical projection of this, so you will get this much. Again if you get this and you take a vertical projection like this, then you get this much of area. Again you take this, then it will get this, and similarly if you keep continuing doing this, taking the projection, and if you sum everything, you will get this line. That is how it works. Now you see that when you do the paneling, then we already know how to get the area, we already know how to get the normal to this to that panel. So I can take only the vertical component, which is nz, and multiply with the area, that gives me the water plane area. These are the very important, and also it has to be correct. I mean, it should match with our formulation, because our entire code later on based on this geometry, based on this normal. So, even if something wrong to getting this water plane area, it is consistent with the our coding, because I am using my own panel, I am using my own normals, right, which the entire code is written in that particular normal. I mean, so if something wrong there, it may be wrong, but it at least it is consistent with each other. Only thing we need to figure out that when you do the basic thing, the paneling, the normal should be correct, or it is the outward down normal. It won't work. So at somewhere you will get this downward the normal. Normal should be uniform, right? Okay. So that we have to be careful when we define the normal. That's why I keep telling you, make your all the normal unified. Okay. Now this is to something is very trivial, and then this coefficient C33, C35 and C53 also. In fact, in that case I would suggest you can use the that what I have solved for that C33 is fine, C33 is equal to rho G A W P, right. Now, in case of a C35 or C35 especially C35, it is the moment about the water plane area. So, it is better now from this panel type, again you just figure out at that points at z equal to 0. So, I just select only these panels, because I only select this panel, and then from that I can select these points, and then I can do this C35 stuff, that what I have done for the strip theory code, and similarly I can get C55 also. So, C335 is minus rho G integration over the length, which is x into y, or you can say b into dx, and it is equal to minus rho into G integration L, it is x square into y dx. So that is how we can get the values C33, C35 and water plane area. Okay. Now, in next level what is important, that to match your mass, it is very important, right. So, to match your mass, what you need to do is you have to have a hydrostatic force a priori, and then you need to check that your m into G should be equal to this hydrostatic force F. So, how to do that with respect to the panel method, that is also very easy. Now, again I am drawing this. So, now I have a panel, right. So, now once we have this panel, then I take this point, let us say called the centroid of this panel. So, then I calculate what is the hydrostatic pressure So, P is nothing but minus rho into G into Z. Remember that Z, this is, if it is Z is positive upward, right, and Z is negative downward, right. So, and then this is the value at this level is Z equal to 0. So, you should remember this, right, because at the end this minus and Z also minus become plus. Okay. Now, thing is that, so this is the hydrostatic pressure at panel Pi, and then you need to multiply this with the area, right. So, this is the area, and then if I try to figure out that if the weight should be equal to the buoyancy, so it should be multiplied that the Z component of the panel. So, this gives you that the Z component of the IF panel, right. So, what I do? So, I just use minus rho G Z I of this particular panel, then multiply by the area of this particular panel, and then I multiply the normal component. So, that means the projection again, and then if I add, so let us say it is I equal to 1 to n. So, if I do this F Z I, that gives me the total static force. Okay. So, now we need to check that m into g equal to f. If it is not, suppose sometimes what you are going to do is, you are going to take this input m from the code or some input. So, like when you do the design part, you do the design. So, that time this all the specifications is given, right, like there is a shape, and in that shape, then you know that what is the displacement, that means the weight, and you know all this length, the breadth, everything is given to you. And suppose you are not that what is it that like little bit go with the convention, like I should take this mass. Okay. I would say little bit conservative on this hydrostatic part. So, and then you are taking, okay, this is my ship, this is the design. So, I must take this m which is given to me from the hydrostatic table or the design office, right, or this hydrostatic particular, when they calculate, they give you this mass, and you say that no, I am going with this mass. Now, however, when you do the paneling might not be that great. Okay. Why I say that great? Because at the end, that a curvilinear surface you are modeling with the planar panel, right. So, when you do this curvilinear surface modeling with the planar panel, and then you have to make the panel is sufficiently small, so that you can have the minimum curvature over there, right. So, that means even if like the high curvature like this. So, if I ask you to draw this curve through some straight line approximation, so then you need to make it smaller. So, at least you make sure that each individual section can be approximated by the straight line. Now, suppose you are having some 200 meter or 250 meter long ship, and then there is a curvature is always there, like along, at least not even if not along the length, definitely they have a curvature along the draft. So, that means in direction of z, definitely. So, then suppose if you want to make sure that this curvature can be approximated by the planar element, so definitely you need to discretize the shape with ample number of panels, like some 2000, 3000, 4000, right. Now, once you do that, now we are again going to discuss later on, and already we have discussed in the last class also, we have a convolution term involved in the dynamic calculation. So, it means that at each time, at each moment, you need to calculate the force from the t equal to 0 to t equal to that particular time period. So let us say about the 100-second, what is going to happen? You have to calculate all these 4,000 panel thing, that dynamic force or whatever, from t equal to 0 to t equal to 99. See, that gives you the time. It is so time consuming that you really can't afford it, right? So normally what we do is we make little bit compromise on the paneling. So we grossly, because see here the point is that we are at the end we are replacing this geometry by the number of sources, right? That is the essence of the boundary element. So in a way we really don't want that rigorous paneling, because this paneling or these things only important for the geometric calculation, like areas, like this source is associated with the area, right? So it is really that not sensitive towards the correctness of the paneling, right? So therefore often we really do not replicate exactly the same geometry by improving lot of mesh, lot of panels around the body and make a perfect body. We don't really, that is not our focus. So we compromise on that. So what we do is we use some 800 panels to 1000 panel, mostly normally we do that for modeling of the geometry. Now when you do that, what actually we are lacking, that geometric, some definitely when you do that modification, the first effect is that if you try to calculate the area or volume under that body, it cannot be same, right? Now it does not affect on the hydrodynamic side, but it has effect on the your at least from the hydrostatic point of view, because if you try to calculate the volume of a circle, and if you take only very less number of points, and if you try to approximate this by a straight line, a polygon, then definitely the area is not matched, right? If you just in other side, like this is how people going do this polygon to find out the area value of pi or so, that is another story, let us not go into that. But the idea is you need multiple point to closer and closer to the circle, that is the idea. So here where we compromise here on this volume. So now essentially if it is compromised that the volume is not equal, so definitely the hydrostatic force or static force is depending on that geometry. So geometry cannot give that static force not necessarily matches with your displacement that is given by the your the design office or the design. So if you don't make this happen, then what is happening, I discussed at the beginning, at t equal to 0, you have definitely you are going to have a unbalanced force, and that cause your numerical instability. So therefore idea is you do the static calculation, it is very easy, right? Only rho minus rho g z I into area of the panel multiply normal component, this gives the static force at that particular panel, add thing, you get the total static force and you match with the your input mass. If it is not equal, then do not go with the input value that is given by the design office, then you should go with this hydrostatic component as your weight. So this is this is the whole point of discussion of spending much time, because it is always very important at the static level t equal to 0, you have to have a static balance, like mass should be equal to buoyancy, that water plane area, the all the component that you are measuring from with respect to your own definition. Okay. So with this we stop over here. Okay, and in the next class we are trying to discuss something on the dynamic part. Okay, thank you.